So with that, we can get started. Let's see, I think I need to turn this off as well. All right, so previously we talked about linear regression. We overviewed all the concepts, most of the concepts in the statistical machine learning. We started with the supervised learning, unsupervised learning, then we deep dive into the linear regression last week. This week and the week after, we're going to talk about classification. And if you remember, the classification is a method of supervised learning. So we have some labeled data. We're working on the labeled data in order to find the best fit for the model. And we will going through a bunch of, how many, maybe 3, 4 different classification methods to see what are their differences, how we can train them in R, how we can get a sense of their accuracy and such, and what are the concepts involved in classification. Next week, we're going to cover more of them, naive Bayes, KNN, and I believe we have 2 more classification methods that we will cover, and all of it would cover chapter 4 of the textbook. So that would be the items that we will be going through. For classification is basically, we want to predict a categorical. The difference between the classification methods that we have and the regressions is that we have a bunch of different categories. We want to be our response variable. So you remember for the regressions, we wanted to have a numerical value, whether it's like 1, 2, 3, 4, and such. But if the question that you're solving, the model that you're training is about whether a flight would be late or not, it would be a binary thing. So we have 2 categories. It's not just a single number. Or if we want to see a tree is infested or not, that's yet another example of being categorical. There are other examples of that, whether you want to find, for example, you're working for a restaurant that they want to know when someone calls which of the menu items they've chosen. So it's more than, it can be like expanded easily beyond 2 response variables or 2 categories, which is the binary ones. So we have a notion of binary classification models, and the ones that are expanded on top of that is multiclass. And there are examples of that. I believe you have examples in mind, but can you have some examples in mind from the binary class, other than the ones that I mentioned, obviously? Any classification problem that you faced or you think would be nice to solve? Fraudulent transaction, exactly. Which is one of the domains that I like a lot. Anything else? What about the multiclass one? An example of multiclass. You can guess about anything. So you can think about any binary classification model can be easily be turned into a multiclass. So fraudulent transactions, it can be divided whether it's fraudulent or benign, or it can be expanded into it's a benign, it's a medium level risk, is an immediate threat. So you can easily think that it can be expanded into 3 or more different categories. So that's about the type of different classification methods that we can think of. One of the main classification methods that we will go through is the logistic regression. So earlier in depth we talked about linear regression. I'm not sure why this thing is not working. Anyway, one of the methods that we talked earlier about is the linear regression. One would think that linear regressions could be also a candidate for solving classification problems because we find a line, and within that line definition, like the picture above, we can come up with some ways to break it down into 2 different values. So if our data points, x, basically the observations, are here and there, and we want to make a classification method out of a linear regression model, you can think of that we can find the line that best describes the model and then break it down and say that if the values are above whatever, 0.5 in this line, for example, we call it as class 1, and if it's below, we call it as class 0, right? But there are issues with that. We can do that, but there are limitations with that. One of the limitations that we have is that linear regressions easily get out of bound. They can be negative values, they can be super high positive values. They're not necessarily between 0 and 1 to be meaningful for us, to have a distinction between, and there's no logical way to split them into half. So you cannot necessarily find which one's at the half of it, right? So that's one of the limitations that we have. And the second one, they don't necessarily estimate the probabilities of which class might be highly prevalent or not. So these are the two main issues with finding or basically fitting a linear regression model for a classification problem. And also, if we know a tool, we shouldn't stick with it for every single problem. So there are better ways, there are better models that we can think of to solve the classification models, for which we'll talk about the logistic regression. So earlier for the linear regressions, we were finding a linear relationship between the observations we have, between the independent variables that we had in the response, which was a line, right? In order to make sure that we have the situation we wanted to have for classification model, which is being between 0 and 1 and have a good sense of probability of the different classes that we have. Here we rely on the logistic function. The logistic function, the output of it is always between 0 and 1, and it helps us to achieve the goal that we had for classification. So the same relation that we had between P of x, which was a line in linear regression, everything maps into logistic regression as well. You can easily see that part. The fitting process of finding the variables for that is called maximum likelihood. But as far as I looked at the course materials and such, we don't want to really get into depth of how maximum likelihood is working. So I stop at there. But the good thing is that R is going to do that for us, and it would train the model for us, but we know there's a mechanism behind it, how it is optimizing different variables for that one. There's also another notion. So if you look at that, we don't have a linear relationship between our x and y values here. In order to kind of simplify that, you can play around the formula that you have. So if you times p of x on one and then e to the power of line variable, and this one goes on the other side of the equation, and you get a factor from both sides, you will reach to this equation, which is called odds of the probability. So I guess you can imagine how it works, or I can write it down on the whiteboard if I find something there, right? So we can get the p of x equals e, I will call it a, 1 plus e a. If you times it, you're going to be p of x plus p of x e to the power of a equals e to the power of a. Then what I would do is take it there, e of a minus p of x e to the power of a, and then it would be e of a 1 minus p of x, and then if I divide both, yeah, it would be p of x equals e to the power of a. So here's the process for obtaining the odds out of that. And then if you remember, if we get log of e of a would go behind, log of e is 1, it would give us the a. And that's what we would call it the log odds. The log odds, or logit function, is basically giving us a linear relationship between our independent variables and the response, just similar to the linear regression. Basically the odds will give us a sense of like how likely is, for example, for a transaction to be fraudulent in a data set. So depending on the variables that we have, for example, the log odds, for example, or the odds themselves, they might be like 0.8, something like that. Then you can use the variable here, the formula there. If the odds are 80% normal, then you have 80, 0.8 over 1 minus 0.8, which is 0.2, then it would be 4 times likely for a transaction to be normal versus the ones that are fraudulent. Which is an interesting concept in the fraudulent transactions. I don't think we go over the unbalanced data situation in the classification modeling, at least this session, but it's a concept that a lot of problems suffer from. So if you think about it for fraudulent transactions that Chris brought up, there's an issue that only like 2% or 3% of transactions are fraudulent. So if you train a model that marks everything as benign, it would have like 98% accuracy, which brings another problems and another questions. But that's something that I will get into probably next week. So this way, using the log odds or logit, then we describe it as regression model has a logit that is linear in X. It's just similar. Everything that we go through for logistic regression is basically we are kind of mapping it back to the linear regression that we had for the regression problems. So that's also similar to that. We can expand, just like earlier. Do you remember about having multiple variables in linear regression? Here we can also expand on that. So X is not just one variable. We can expand on having multiple X's, X1, X2, all the way to the XP here as well. And also, we can think about having, instead of having like a binary, we have a multinomial logistic regression. So probability of a class, a response variable that is y, is not necessarily 0 or 1. Here it can be k different values. And for that, we have basically different coefficient for each of this. So we have a variation between the coefficient that we have for each of those classes and also for the input values that we have. So let's stop at here. Linear regression, we went through, it was just a line. We're trying to fit it in our data as good as we could, right? Based on the errors that we had based on our training data. And then we had the formula for the line. For logistic regression, still, we have the parameters that we need to find, the coefficient there. The formula is slightly different. The model is slightly different, and what it does is that it's trying to cap the values it finds between 0 and 1. It's basically using a sigmoid function. Let's try to see if we can do the same things in R, and if I have everything here to do it. The way that we want to do with different set of data into this class. For those to work, we need to install the NYC flight package. You can also do it with me. You can install the packages, we can run it together and see how it does it. And again, we see the similarity between the data, the process of working through training the model between logistic regression and the linear regression. The first thing that we need to do is to install NYC. I already installed that, I don't need to run it. I just load the library in there. And for the data, when you load the library, there are different ways that you can, I think we need to do data flights. Should have bring me, I'll do that, I guess. Yeah, there we go. So you can take a look at the different data sets that you have here in the library. Just make sure that you have installed the package first and you'll load it. Similar to anything that we do in Python, there's also equivalent values functions for R as well. We can get like a head of, what is it called, flights. And one of the ways that I like a lot when you don't write it down completely, it has a better visualization in R. So it's easier to take a look at it as a data frame, which you used to see in Python that way. So you see what are the attributes are in there, what are the sample values that we have, some of the sample rows, a sense of how many columns we have. And also head gives us the first 1,000. So you can take a look at the first thousands of them, I guess. All right. So I would get the head of flights, or this is yet another way of displaying it. However, as you can see, it just prints the first couple of them, not a couple, the first 5 of them, and then just describes what else is in the data set. Anyway, for what we are doing, also make sure that you include or load tidyverse so we can use pipe and other functionalities as we are working with the data. After you've done that, what we want to do is do this 3-part to create the data that we want to work. What it does is that we want to join the flights and weather data together so we can have a sense of basically different variables, different features in order to describe if a flight would arrive late or on time. So there are 2 different data sets in this library. We have the weather, we have the flights, and the common point between the 2 is the date information and the origin. So it's a location and date time, which is year, month, day, hour, and origin. So if you do a join, an inner join between the 2 data sets, between these 2 attributes, it will give you a single data frame that has the information about both flights and the weather. And what we do is that, again, if you remember from the earlier sessions here, we have the flights, we pipe it there, we do the inner join by a weather data frame, and then pipe it there, and then we create an arrive late label. If the flight has any delay, arrival delay, we set the classification, we set the label for it to be arriving late. We can run it, we can get a head on flights, weather join, and you can see that we join based on these 2. Then we have information about the temperature, about the humidity, air gust, the possibility of rain, pressure, etc. in a single data frame. That was the goal of the comment. After that, I was trying to run the comments from the course material that I also shared last week with you. I think the part that I didn't figure out is that we have some null values in the data frame because of those. When you train the model would automatically ignore those rows, and then you will have a mismatch between the data that you'll do the prediction for and the actual labels that we have. So I try to do some cleanup to make sure that they work seamlessly. That's the part that I'm doing. Probably in Python, you remember fill NA on pandas would do the same. It's basically doing the same. Fill NA would fill them with the value. Drop NA would do the same that NA.omit do on R. So basically, we choose a smaller subset of data frame that don't have any null values. And then, if you remember, linear model or LM was doing their linear regression in the earlier sessions. Here we are using the GLM. So we join the data as kind of data preparation step, right? And then we do the data cleaning step, just like a small one-liner. And then we train our data, turn our model. After that, what we can do is to get a summary of the model, and the situation should be familiar with what we've seen before in order that you see the comment as well. It's basically we have the relation between pressure, departure delay, And we are training basically a binomial one, whether it's arrived late or not. Here again, the variables that we have, the parameters that we have are pressure, departure delay, the intercept, and then we have the p-values. Same situation as a linear regression, so we can get a sense of whether the variables that we chose are important, are there strong factors for making a decision whether it's late or not. And then we get the information about the residuals as well. Anyone remember what's the degree of freedom on the model summary? Or how it is calculated? So the degree of freedom is kind of just to review concepts that we went through. So the degree of freedom is basically showing the number of data points you have in your data minus the parameters that you are using to train the model. Gives you a sense of, kind of the trade-offs. Not the trade-off. So imagine if you have 4 data points and you have 4 parameters, the model should be a little bit different than having like thousands of data points versus like 2 parameters. So that's what it shows, the different combinations that it has, or on the other way, is the degree of freedom that the model had to train. And the main reason that we have all of these is basically later in the actual world, you want to take this summary and be able to compare the models, different models that you're training, and then making a decision which one is improving the results and which one needs to go to the production used in your product and such. So we have trained the model that way. Now we have a logistic regression. Nothing has changed almost from our perspective compared to using a linear model. We could have just used LM instead of GLM to have a linear regression model. And then if you want to make a prediction, then you can use something like that. So you can use the predict function, pass the model that you trained here, and then you pass a tuple, which is the 2 parameters, the input variables, the independent variables that we passed to our model, which we used to train the model for, here and here. Pass the values, and then ask for the response. When we run it, it will give us the probability of the model 1. So the response would be 1, and probability of that is super high as well. Then we can do it for all the lines using this one, not just passing one of the tuples, doing for all the data points. And then I'm doing the confusion matrix. So the confusion matrix gonna look like this. I think we briefly touched on confusion matrix maybe on, I don't remember, last week or the week before. So we talk about the confusion matrix, what it shows. It shows that actual labels, so it depends on how you look at it. So it's actual labels and what we predicted for. And basically what it shows is that where our model is performing well and where it's not performing well. Basically, if the actual label is true and we are predicting it to be true, then we have true positive. This is where the model should have most of the data points in. Or if it's false and we are predicting it to be false. So it would be these parts, true positives and true negatives. These are the parts that your model should work really well. And these are the parts that you should work on your model. Whether it was a late arrival and we said, no, it's not going to be a late arrival, or the other way. If it wasn't and we said, oh, it is. And depending on the problem definition, each of these two might have a different weight. So back again to the fraudulent transaction classification model. So if you say for a normal transaction, to say that it's fraudulent, that has a different weight for your business, because if you keep marking everything as fraudulent, what it means is that actual transactions of customers going to be rejected. So it would add to the chaos and user unsatisfaction from the experience of that. On the other hand, if you miss only one fraudulent transaction, it means your business has lost the amount of transaction, for example. So depending on how you define your classification method, these have different weights, and you can set those weights when you're looking at the accuracy of your model. The confusion metrics give us a good sense of, like, visually we can do that. So you can know how your model is doing, how it's performing comparing different models, but you also have different measures, different criteria. So you can use that, look at the accuracy, you can look at the recall, the sensitivity of the model, true positive rate or false positive rates. So I created the confusion metrics. In the course material, we'll just look at the mean value of, like, what fraction of predictions we had were accurate. It's basically the accuracy part. So 78% this model is working well. But you can also either use the library in R, I think is named Caret. So it has all the, like, the accuracy or all the evaluation metrics already. Or you can just get the values yourself. So we do them all. So you can extract the true positive, true negative, false positive, false negative from the confusion metrics, given the indices. And then you know the formula for accuracy and the formula for false positive rate, for example, and then calculate those. So you see the pure accuracy that we have matches the one that we calculated easily there. But as I mentioned, again, depending on the classification method that you're looking for, accuracy is not the only thing you have to consider. Just wanted you to have that in perspective. And always remember, when you're looking at the model accuracies for different models to measure, always remember that the 90% accurate, 98% accuracy can be achieved on a problem that has only 2% true label. All right. So that's the part that we wanted to cover for logistic regression. Now, what I'm going to ask you is to do this part. At least a start on it. Try to. So basically what it wants is that earlier what I did is that created the whole data, work with it, train the model. Now we want to have a notion of training and test, or having more recent data. So you need to do a little bit tweaking there. And then we can continue doing it together. If you're facing any problem, let me know. If any of the commands that I ran earlier doesn't work for you or doesn't make sense for you, or it's not just exciting as it should be for you. Any of these items, let me know. So these are the comments that we earlier executed, from installing the package that we are using to the usage of the packages, forming the data, training the model, and then using it. And if you need the practice activity question, is also in the course materials under week 3. I guess it might be helpful to see the comments first. So, were you able to get the data from more recent months? Is the question asked. I'll also share the run history again after the end of the class, if it helps. All right, let's do it a little bit together. So what the problem is asked for is basically doing two things differently than what I was going through, right? The first thing is splitting the data into just getting a portion of data based on the time of it, right? And the second part is to splitting the classes. So if it's late or not, versus if it's very late, it's not late, it's a slightly late or very late, kind of like that. So in order to make the data, what we can do is do something like this one. And what it does is basically breaks. This is the part that you want to do. So when you do the mutate here, earlier we were just saying mutate, making it, where was it? Here. If it's more than 0, just make a class, whether it's late or not. Here, what we are doing is basically giving it into the different bands. If it's late between infinite, negative infinite to 0, it's not. And then if it's 30 minutes late or more than that, so these are different classes that we have. And then it will create the data that we have. Then we have a couple of, well, for multinomial, you could have gone with the normal ones for now, just looking at that. But for multinomials, we can also install a new package, nnet, and then load the library. But let's fix the, before training any model, we can also look at the way that we are getting the newer months. So we pipe the data flights that we have, whatever data set that you have. You can choose the months that are before some values or more than that. And when you're working with month, again, something that you want to make sure is that your data set is not having multi-year data, right? Otherwise, you could have get the second half, for example, the second half of different years data, which is not good. Anyway, we can start from here. So this is the way that we should have prepared the data and then getting into training the model. So I have the data, I have the package that I want to use. And for multinomial, instead of GLM now, I'm using a multinomial. And I'm training the values. Just like neural networks, which have different iterations or epochs, here it also goes through multiple iterations because there are a lot of parameters that need to be optimized. So it goes through different those epochs until the optimization variable is converged and it stops at that on multiple iterations. And then we get the summary of the model. You get a sense of the coefficients, the standards, errors, and then the residuals as well, kind of similar to the other values that we have. You can do the predict similarly, and then you can get the values, and you can get the tabular view of that. As you can see here, instead of just late, not late, false and true, we have not late, late, and very late. So 3 different variables, 3 different classes, since it's multinomial ones. And then we can also get the accuracy of that. If you remember, the accuracy earlier was like 78%, now it's 75%. It's a more complicated problem when you have 3 different classes instead of 2. It's easier to have a cutoff somewhere. But it doesn't mean that your accuracy cannot expand. Remember that the only variables that we are using is basically departure delay here. So, getting back to the problem that we were solving, if we want to do the same situation, the only difference that we need to do is using a different training and testing data and also relying on different predictors. More predictors here. Let's do that. So let's create the training data. So our training data going to look like that for months before 7 months, July. And then the test going to be more than that. Do you know why does it matter that our training and testing have a logical order? If it's time sorted, does it matter that train be used on the earlier months and testing on the later dates? The question is, does it matter if I swap the training and test data sets here? Would it train a different model? Sorry, what was it?
Oh, I said it matters because it's time series data.
Exactly. So the data usually, you can also think of it as a time series. The relation, so time series are, that's true, it's a time series. For a specific time series, they are really coupled into their time stamps. Here, if you don't really care about like which month of the year it is or which day or hour it is, overall, it's also important because data sets they have, data has a trend in it, right? So the notion of training and testing data sets is basically to know what we know, give it to the model, train it, and then test it on things that we don't know or haven't seen. The notion of test data is basically data that we haven't seen. If you mix them up, randomly select the data points, give it to the model, basically you are giving some hints from the future to your model, which is not fair or reasonable when you want to test it to see if the model is generalized enough or not. And also it wouldn't give you a concrete sense of how good your model is. So if you have a sense of seasonality, if you have a sense of how over time your data changes or shifted or drifts, then it's really important to choose the right testing and training data sets. It would be helpful for many different problems that you solve. And then, as I mentioned, multinomial from NNet library, we're using it, but this time we are using the origin, distance, and departure delay is mentioned for the list of predictors to train the model. And now it's converged. We make the prediction on the trained data, 75%, and do the same on the test data. Not bad. Slightly even better on the test set. What I'm looking at is that you can compare the models. They are slightly similar, right? Same model on different data sets. What you can take a look at that is that in the confusion metrics, you can get a sense of in testing, in training versus testing, which classes were not performing well. So apparently on test set, what we are doing better is on the late and not late. So these two, we are kind of outperforming a little bit. But on very late, we're not doing well on the test set. So these are the items that we look when we are training, when we are testing our models. Then the question also asks for a reduced model. As we talked about it, a model with less parameters, if we get the same level of accuracy, is always preferred because that's simpler. We don't need to confuse model with too many different predictors. So we can try it. Or do you remember this mechanisms of using less features? What was it called in the previous session? When we talked about feature selection methods? Was it forward selection? Backward elimination? Yeah. So one of the ways that we called it, one of the names that we called it was backward elimination or selection. I'm trying to review the concepts here as well because those are super similar and it's important that you remember them all. So anyway, so we went with a simpler model here, only used 2 variables, 2 predictors instead of 3. Departure, delay, and distance, regardless of the origin of the flight, where it was originated from. And how's the model doing? Is it better? Is it worse? How can we say that? Okay, I thought I'm distracted today. What happened? Was it the long weekend? All right, so what we're looking for, or maybe I'm confusing you with all the back and forth in the code. So here, what we looked at basically, we splitted the train and test data sets, trained a model with 3 different predictors. We got some values out of it, the accuracy on train, the accuracy on test. We made the decision relatively from the test and the training accuracy and the test accuracy. At least I think the laser works on this one. There we go. Alrighty. So here we have the train accuracy and then we have the test accuracy, and based on that we could have concluded that although the accuracy of our model is not golden, it's not like 98%, it's just 75%, but it's generalized enough within that accuracy band, right? So if you are happy with the accuracy level, we can kind of ship it. So that's the product that we want. Then we thought that, wait a minute, we might be able to train a model with even less predictors, so it's simpler. And then we tried the accuracy of that within the same band. Then we said, okay, we could have go with a simpler model. And you know where the simpler model is really important? When you want to ship it on the devices that cannot perform on larger models. One of the ones is when you want to ship it in an application, on a mobile application, it's really important that you want it to work offline, for example. So it's really important to do it. Or when you want to use it in a car as it's doing image processing. So it's always fun to have more predictors, always fun to have a larger model, but when you have limitation in terms of devices that your model gonna run, or the other way, if you're running it on the cloud and you're paying for it. Also, you want it to use less resources because you're gonna pay for the resources that you use. Your customer grow, you have to save money in order to keep your business profitable. So that's the whole story there. Any question before we move on? You'll probably see in the part that I'm going to use next. Any question? Classification? Do you rather we go back and use linear regression now? Easier, more straightforward? But I guess these models are pretty good though, now that I guess, is that as we progress through different models, going through them, we kind of add a level of complexity to the models, but also the benefit of being more capable of addressing real-world problems. Alrighty. So that's the first part, half of the class. The second half of the class is a little bit slightly more fun. I guess I'll go through the first part of it, since I feel you're not as sleepy as you should be to have a break. So let's cover the first part of it, and then we will have a break, all right? Another classification model is LDA, Linear Discriminant Analysis. LDA basically has some assumptions in it. So if the late versus not late classes that we have, they're following the same distribution, but slightly different. So here, for example, don't look at those two plots. We're focusing on this one now. If with only one predictor, if we assume that different classes that we have, the class green and the class pink, they have different distribution. For example, they are the min of -2, a standard deviation of is 1. And here we have the mean of maybe it's 1.5 or 2, something, right? And the standard deviation of 1 again, these two classes. Then we can think of having a class that can have the distinction between the two. It just helps us to know based on the probability of that. Help us to have a distinction to say that, all right, if the variable lies here, I know their distribution, so I can decide if the variable is here, the observation that I have, I can easily say that it's probably for this class. Or if it's here, I know that's higher probability it will be relying on the other class. So it's a matter of knowing the distribution. So the model has some assumptions, the LDA. And if you look at it on, this is for one predictor, it's like for one X. If you expand it into two x's, it would be 1x, x1, x2. Then you would end up with a visualization like this one for two different classes, W1 and W2. What the model does basically, underlying way or mechanisms that the model works, is that it would project it into a 2D shape like this one. So you have the probabilities around the data. And then what the model needs to do is to find the decision boundary. And the decision boundary for the LDA is a straight line. It tries to find or separates, something like this one, separates the distributions. So again, everything that we talked about linear regression kind of applies here as well. Only we have the binomial here, right? There's like two classes, a single predictor. We can expand it to having multiple predictors here. As you can see, it's still binomial. Or we can have it three different classes. And then here the boundary is going to be different. So that's the concept of having the LDA, basically. Again, having some assumption that they have similar distributions. They call it similar covariance matrix. Following the same distributions, but the distributions are different enough that we can make the distinction between them. Let me go through the codes for this one too, and then have a break. So this one, again, similar things. We use a class that provides the model for us. We train the model on the data that we have, and then we see the summary of the model. That's basically things that we're going to do in R over and over. So for having the LDA, we have to install the package mass, and then load it. We have the arrive late data already. We have the flight weather join data frame that we had already, right? We train the model. We get the prediction out of it. And then we get the table. How is it doing? Is it doing better than our previous models? It's almost the same, right? The earlier ones, they were around 75 accuracy-wise. But remember, I think the first one that we trained was 78%. That was a very simple logistic regression one. Not this one. This is a probability of only one observation, but this one. So it was 78%. We learned a lot of new concepts to bring our model accuracy 4.4% lower. But these are the complex models, so we need to play around them, and they have some assumptions in them. Whether both of the classes have the same distribution, we haven't checked that for our data, but we are using the sample model there. All right, so that's the notion of LDA, logistic regression, binary logistic regression, and multinomial. The three concepts that we went through so far. More coming. All right. So let's have a break now for like 10 minutes and then be back for the rest of it. Not much left, but with the same concepts. All right, I guess we can get us started for the second half. So for LDA, just to review a little bit more, talked about the logistic regression. We went on expansion of that. We got to the LDA. We went through the way that we trained the model using the mass library. Now, I'm going to ask you to do the same thing that we've been doing, but this time with LDA on your own. And then we try to see how your models do. it's really important to have the hands-on experience. So you start doing things because looking at the way that the model is getting trained, you will know how these things are getting trained. It's a simple function call with a number of parameters. But as soon as you start doing it and start thinking about why it doesn't work that way, why don't we pass this one, you get to learn about the way that you are using it. So if you have the experience of sitting next to someone who's driving versus you drive yourself, you learn the destinations and the path better when you're driving. That's yet another analogy that I can use. All right, so who is actually working on the practice? Awesome. Good. And who got over the first part of it? Relatively? I would accept if you thought about it too. So if you ran the R code in your mind, that's accepted too. So if you remember the train data, it has the data from January through June here, right? When we chose this part of it, from January onwards or before July. So if we try to do it, we train the LDA on that one, make the predictions, and then create the table, the confusion metrics. So you're gonna get something like that. Does it roughly aligns with the accuracy that you got? Perfect.
Why do we don't have predictions for the
After June?
Yeah, there's no predictions for the late.
For the, oh, here?
Yeah.
Oh, I see what you mean. So for this one, good catch. Because our LDA just doing it binomial, I guess. Let me try to see. That's actually a good observation. Let me make sure that we didn't. Earlier we had a good model there. Oh, because I believe that earlier we were using the multinomial here, right? Let me make sure LDA doesn't have any. I think we also had something like this. Yeah, forget it. All right. So let me see. The direct answer to your question is that I don't know. But I will look into that. So I don't want to pretend that I know. But I was trying to get into different reasons for that. What I want to make sure is that we haven't missed any parameters for the model, just like similar to the earlier ones that we had binomial, multinomial. If not, one possibility is that our model is not doing well, taking care of multiple different criteria. But I will play around it and share an answer to your question. Very good catch though. And that's that should explain also the reason that we have the lowest accuracy ever here as well. So we'll take a look at that. And then we can get the prediction on the test. Same situation here, so probably let's see, departure delay, distance, origin. What we can do, what if we train that on the origin part just to check. Yeah, I will get back to you on that. All right, so I know when we have an open question, it's hard to move on, but let's move on. And I will share in the announcement. Do you get notification for the announcement I sent in Canvas? So you see those ones that I'm sending? Perfect. So I make sure I send an update there, so everyone knows. Thanks for bringing it up. I love it when I'm challenged that way, so at least after the class, sometimes I look at the videos and I realize that some of the things might be missed. It gets me a little bit sad that nobody brought it up. I also think that you guys are so kind, but bring it up. All right, so LDA was one of them. We got the worst model with LDA. That happens. Depending on the data that we have, different models perform differently, but also know again, we'll get to the bottom of why we are not getting the multiple class detections, but LDA has a strict criteria for being able to work on the data. One of them that I mentioned is that it assumes that the different classes that we have, they share the same covariance. So basically they have the same distribution, and it tries to find them, just find the boundary. That's the reason that we have the Quadratic Discriminant Analysis, or QDA. QDA fixes the problems for LDA. And the way that it does is that it doesn't necessarily requires that the two classes that we have, they share the same distribution or the same covariance matrix. So basically they can be from different populations, so the population metrics that they have can be different basically different distributions they can have. And then when you map them to the 2D world, you see that here the two classes might be identical, might not be identical. But also another difference between QDA and LDA is what is the other difference? Can you spot that?
The decision boundary is not straight.
Exactly. The decision boundary does not necessarily need to be straight. So in this case, and in this case, do you remember the decision boundary was straight in the previous one? Here it can be curved. And do you remember something similar like that we discussed? If we discussed something similar like this one in the second or first session, when we were discussing linear regression. What was it?
Like linear versus like logistic.
Yeah. It might be true. So we talked about the line that we had versus polynomials, right? When we have higher degree of polynomials, we were able to fit we were able to fit the data more closely following a polynomial because it gives us more flexibility, right? So here's the same idea relies here as well. So you see there is a lot of similarity between them. Even the name suggests that, right? Logistic regression versus linear regressions. We started from that. But all of them, they have the same concepts. So QDA versus LDA shares the same concepts of linear boundaries versus curved or polynomials. They have it here. But same questions would rise here is that we have more opportunities to fit our data better here with QDA. But what does it mean? What kind of error will we have? It brings up all the discussions that we had about bias and variance and overfitting. So it's all applied here as well. It gives us more flexibility, but it means that can be suffering from the overfitting here as well. So that's yet another thing that we need to consider. For QDA, I guess on the practice we can do together too. Would be similar again. So we have, instead of LDA, we use the QDA to train the model. We use the same data. We train the model, get the prediction table and the accuracy. And then we have the 78% on this one too. Make sure that, yeah. Which this one, I believe, if not outperform, is matching the first one that we saw, the 78%. I think the first one was 78.6. Let me make sure. Well, 78.8. So, good job, regression. All right, so that's for the QDA. This time, let's do the practice. Again, we're using the same training set that we've been getting from month less than 7. This time, predicting the QDA. Let's see if this time it's getting the Sure. Oh, this one?
Yeah.
You figure out something about the reason it's not giving all the labels? For the practice, you mean, or you mean the multinomial ones, right?
Just yeah.
This one. What were you thinking? What were you thinking?
I just made a syntax error. I wasn't sure what.
Oh, I see. I see.
Just a syntax error.
No worries.
Yeah, thank you.
Sure.
For the LDA, is there a way to check the decision boundaries, like the actual numbers, for determining how they're like why they're slotting it in, not into the zero column? Like, what's the decision boundaries for not late, late, and very late?
It's a good
I don't know
thought.
how to pull up the numbers.
Me neither, but let's give it a try. Let's see if such a thing exists in R. I think we got the summary of that. What was the name? That tray. That's actually a good thought. From what I'm seeing, if I'm interpreting it right, it's actually looking for two classes. It's actually looking for two classes. If I'm interpreting it right. And it's funny that it created the same, also didn't mention it, but these models under the hood, what they create, they also create the dummy variables that we talked about when we were discussing linear regression, when we were looking at the interactions between different variables. So here it does it the same, like the origin JFK or origin LGA. I'm not sure which airport code is this one, but it creates the dummy variables for those as well. So these are the actual coefficient. I believe there's a way to plot them. Not sure how easily. Earlier we were able to do it for linear regression with the plot directly on the model. But it doesn't do it since the margin's too large. Actually, we might be able to do it on a smaller one. So a smaller one was this one. Yep. It must be the other frame or an object for the predictable. We'll add that to my to-do list. So plotting the decision boundaries, I look into that too. I think from the coefficient, what I'm seeing is that it's not getting the multiple labels. All right. right, for the QDA one, again, we have the same set of processes. Pick the data, have the predictors that we want to choose, train it using the QDA function, get the predictions, get the table coefficient table, and then the accuracy. So slightly better. This time at least QDA is doing it. So we have multiple classes. And since they have the same function signature, so they're passing the same thing with LDA, it just makes me think that our model is doing poorly. So it's not a matter of how we are using it. But we'll see. And then we can do the same thing for the test data. Here to here. Basically use the predict function, get the coefficients. Where's the actual data? Well, what we predicted and the actual data passing. It creates a table and then getting the average of our accuracy. So 75%, 0.7, 75% versus, which is within the same range. I think with the LDA we got 74, if I'm not mistaken. 68. Oh yeah, right. 68. Which one was 74 then? You're right, 68 was because the one that we are missing to, yeah, 68. Thanks for the correction. Oh, 74 was the smaller one on the two parameters. All right, so that's mainly let me make sure that I covered everything there. Yep. So the classification models, especially the first half, in my view, they are the less intuitive classification models. So we split them into two different sections. So we get these ones done, we go through them, and they have a lot of similarity between linear regression and these ones, between regression and classification. Those are kind of natural way of getting into from regression to classifications, and we went through them. They have all the similarity in terms of process we have to take in order to make it happen in R. Except we had some bump there. We'll figure out why. Next session, we're gonna go through more KNN based classification, and two more which I put them in the same family, but it's better not to talk about all of them in the same session. And then we'll be done with the classification models. And then we will get more into the mechanisms of training models, how to deal with different models, data processing and such. So that would be where we came from, where we are going, and where we are now. So next session, expect some of more classification models. I try to put them in the slides in the third row. So overall, when you want to review things, you have one slides to look at, all at the same place. Any questions so far about why we do classification, how we are doing it, how we are doing it in R, what does accuracy mean? No? All right, great. How are you doing with the homeworks? Did you get grades for the first one? How was it? Was it good? Reasonable? I'm not grading, so feel free to say anything. This is a good thing. We have graders. One of the students from the previous class. It's helping.
I just have one question. Like the most recent one, there was like some questions where they ask us to do so much, and it's so redundant after a while. Like I'm just copy and pasting. Are you able to? Like it was the last question, question 15, and all these parts are just had us plot like 12 simple regression, linear regression models. And I'm like, okay, I get it. I get why.
Sure.
And it's just found it very annoying and tedious, and kind of like a waste of time after a while.
Of course. If you feel that way about the homeworks or things that I'm asking on the class, don't do it. All right. We're here to learn. I don't want to waste your time. So if you think that the homework, so do two things. First, question your understanding of the question, and then if you think that the question is really asking about that thing that you're doing, just don't do that. Do one or two of them. Mention that the rest is similar, or the rest goes that way, all right? And if the grader wasn't aligned with what I'm saying in class, bring it up to me, I'll fix it. So we don't want to do that. It actually brings a memory to me. I remember I was in like 3rd or 4th grade, maybe in 3rd, and my teacher came to the class and asked for, it's not the case that you brought it up, it was my mistake back then, but she asked to write numbers in both like numerical and how it is written, like spelling them from, I don't remember the exact numbers in our language. It was pretty similar. It was like from 100 to 110, something like that. And what I heard was from 100 to 710. And then I was working on it for a whole week. And I was like writing things. It was half of the notebook that I had. And at some point my dad said like, that doesn't make sense. You really shouldn't do that and suffer through that. He came to the school and talked to the teacher. Why do you give them this homework? And he said, no, it was just 10 numbers. And I was doing it. But the good thing was that for the rest of the year, she didn't give me such homeworks. So I kind of proved myself that way. But as I mentioned, it's not the case there. But if you feel the problem is that if the question is asking you something like that, just don't do that. And for some of them, I had like questions whether we need to have the interactions between all the variables, or like which variables or predictor we are using from the data frame or such. Just do it for one or two of them, just to see the difference, and that's about it. You don't have to do it. Good point. So you're going to have another homework. As I mentioned, every week you're going to have the homework for the week that we have midterm, which is coming up February 12th, right? It would be same class, same time. I'm not sure, we might still have a homework, if that makes sense, since we have to go through them. But you're also going to have the midterm, so we'll figure out what we're going to do. Tonight I'm going to share the homework to the next homework. And then we'll take it from there. Before we go though, I want to talk to you about the projects. As I mentioned, which portion of your grades the project will be, I haven't set it up yet, but I was so excited to share it with you. And at the same time, I want you to have time to work on it before the end of class, because we are at week 3 and we have only 7 weeks left. And I want you to have meaningful time to think about the project you're going to work on, how you want to work through it and such. For each of the project, if you decide to do it, up to you, again, like the homeworks. If you want to do it, do it. If not, well, it depends the way that I put the grades on. You might lose grades though. So it's better to do it, let's put it that way. For the projects, I have some suggestions. I'll look into what can be beneficial. I think if you do a project that matches the type of industry you're going to focus on, helps a lot. And I tell you why. Sometimes it just helps. It just helps because companies know that you had some exposure to the things that they're doing already. So you proved it ahead of time, even before your interview. So that helps. It doesn't mean that they look for the keywords or such, but it's just helpful. And it's something different. So I like your projects to be meaningful more than doing something for the sake of having a class project. All right. So think about the type of projects you want to do, the title of it, or the actual thing you want to do as part of the project. But what I want you to do is that at the end have something to present, both in class and also keep it as a website or as a tool or as an application. Just think that you have the goal of fixing something for someone, something that actually works. Right? So think about something, making a project or a product out of it. Let's think about it that way. I have a couple of suggestion for you. First one is about YouTube video performance prediction and optimization. For each of these ones, I take a look roughly. There are some data sets already available, so you can take advantage of those publicly available data sets. Feel free to look around. There are definitely way more data sets. There are a lot of contribution to the open source community and sharing knowledge and such lately. So there are plenty of them out there. So YouTube trending data set, take a look at that. That can be helpful. Many of them, they are in Kaggle too. So if you happen to find a good model working on that, you can put yourself on the Kaggle leadership as leaderboard as well. And the second one is the e-commerce product review analysis. Amazon, of course, I'm looking at that. So Amazon reviews is really good because you can define plenty of different ways to work with the Amazon reviews. I don't mention it because I'm working there, but it's really good. Amazon reviews is the main reason for that because it has the rating, it has the number of sales, it has the prices, it has the sentiment on the reviews. So there are, if you think about it, there are plenty of different classification models that you can think of, different response variables that you can think of and start working on a model with. And I just realized that, like last night I was searching, UCSD has a great, like 5 million or more of different products available. So you can take advantage of that. And the third one is sentiment analysis on social network data. I think there's like sentiment 140 from Twitter or former Twitter X platform. So you can use that one. Sentiment is a good thing. You can kind of proxy that to having as a good sentiment, bad sentiment, something like that, or you can have another, have multinomials thing again for your classifications. You can define here, as I mentioned, you can define regressions and classifications if you think about the rating of a product based on different criteria, or whether you're going to be selling well or not, or customers use the product well or not, or what was the pain points based on the reviews. That would be also great. And for the videos, the same. I think depending on what features you get out of the YouTube dataset, you can think about whether the video goes viral or not, how many views it would have, depending on the characteristics of the video on YouTube. That would be another interesting project. For each of them, as I mentioned again, there are a couple of things. I think I noted it somewhere. These are the parts that I expect you to do. So that's the reason that I want you to have at least a group of, I mentioned 6, but during the break I was thinking about it more, maybe a group of 4 would be enough to, between 4 to 6, all right? But definitely not less than 4. And the reason for it is that I want you to have a sense of, I definitely had it through different projects as well, but again, to practice it working as a team, having different opinions, justifying your choices, and then having different ideas and work through that. It would be really helpful. And also, I would suggest try to do your best in terms of using the tools and collaboration tools out there, like Git, of course, and then have probably, if you can, if you want, have a website for the final presentation of it and keep it available as well. So that's a good example of your workload and how you've been working on it. So the way that your project I expect to do, as any machine learning project, is that first choose your topic and make sure you have data for it, all right? So don't think about a really exciting topic that you don't have the data, and I don't think you would have enough time to start crawling the data. And I don't expect you to use like paid APIs as well. If you want, you can, but there are plenty of data sets available already out there that you can use them, so I suggest that you do that. So for next week, what I expect you to see, what I expect to have from you, is that you form your teams. If you have any problem, you want me to assign groups and such, let me know, and choose your project topic. And make sure you have data for it, these 3 steps. Know your group, know your team, topic, and the data set. And then every week, I want you to make progress through the project. If any questions, anything, just let me know. We have to go through data analysis. EDA is really important, and to give you a sense of ways it can be done, I can walk you through. I mentioned the Amazon reviews. It reminded me 1/3 of my PhD thesis was working on Amazon reviews as well. So I guess that's one of the examples that they help. Now I'm at Amazon. So that's the reason I'm saying if you work on a real world project, it would help you a lot as well. But that's definitely one of the reasons that I'm there. So some in AWS, this one is on their website part of it. But anyway, the way that it was done, in one of the papers that we had, it started all the way from getting the head and summary of the data frame or data set that we had. Basically, EDA, exploratory data analysis, is the main part of things, because before you know what you have in your data, you cannot really get a sense of it and expect to have a good model out of it. So as part of your project, you expect to see, you know what you have in the data, you know what are the characteristics of the data that you have, which was another part of the paper that we were working on. For example, here we were talking about the way that we broke up different types of products. Just imagine you have a data set with a lot of different products, how you look at it, how you look at the ratings of it. First, you have to get a sense of different categories and bins of products to compare them in a fair way. Like comparing the reviews for a laptop versus some food materials is not fair, because like the users of it, the consumers are different, and also products that are in different price ranges. So those are also different. So again, this is kind of part of things that is expected to be done. And then I talked about the sentiments and such, is about the feature selection, which we added to the data set back then. And the main purpose of this paper was that, I don't know if you know about it or not, on Amazon you can be a reviewer and they send you products for free. Amazon doesn't do that as a platform, but sellers do that because they want to have rating, they want to be up in the search results, and they will be happy to, instead of marketing, they send you free products and ask you for good ratings. Thousands of people would do that. It would boost the business for the sellers. They would come up the searches, but it's not a fair practice on the platform. So what I was trying to do here was to crawl the data off of the reviews and try to figure out if I can spot those type of reviews. So that was the main purpose of it. It's one problem that basically started when I joined Amazon. I started buying stuff, and one time I ordered like a $2 or $3 HDMI cable, but after that I got like a wireless mouse from the seller for free, and I got like a bunch of other digital items. I said there's something wrong with that, and all of them, they said, just please leave your, it was a thing back then, like honest review. It just triggered that thing that I can look into that to see how wide the scale it is, and I searched on Amazon. I realized that's the largest scheme, and by the time that we did it, I think there was like 5 million or more than that. So anyway, so these are like real world problems that if you're on the lookout for them, you can find them, you can solve them, and this could be part of the things that you do. So the models that we used were able to spot if there was like a campaign for the products, was able to find them meaningfully. Like this ones, we mark all of them as normal, but all of a sudden they started having a promotional campaign, giving free items because they wanted to be top on Amazon. And then we also had some, you see this rating as well. So all the ratings, it was going down. They decided to do something about their ratings and they boosted up. So that was the way to doing it. That's for one product. So that's what I expect to see from your projects as well. Start with the EDA, show me, not me, show the students, show everyone what the data looks like, define a problem and start to tackling it with a good set of assumptions, good models, compare the models, which model worked well, which one not. I think we have something similar here as well. Yeah. So just looking at different set of features, we talked about like backward elimination, forward selection. We did it here as well, like using the basic features and then that kind of adding on top of that, and also using different set of models, and then have a decision based on that. Your final product's going to be based on the best model you find, but the process of getting to that final model is really important. So try to have a good story around it, have a good model at the end, and solve a good problem. That's the main purpose of your project. And also later on when you land a job as an engineer, as a data scientist, as a software engineer, would be the same thing as well. So I hope that would be a good practice then. I do my best to support you through the process. As I mentioned, you don't have to use R necessarily. You can use Python, you can use any other language. I think Python, stick with Python and R. Don't want to use like C, C# and such, or Java for this type type of projects. But with those, you can also have access to good like front end frameworks as well, if you like. Yeah, I think I don't need to go through that. It just reminds me of all the time that I had back there. And yeah, that's it. What I'm hoping though is that you're not thinking too much about the grading part of it. Are you?
For me, it's just the amount, it's the time. It's the extra time that I now have to take out, and because we still have to study and do all the homework.
True.
And it's like, even if you adjust the, you know, the final exam, the homework, and the percentage of it, you still do the work.
Of course, it takes your time.
And so it's just now, it's just another thing, and so it's like, I'd love to do this more than like the final exam, for example.
Right.
Like, that's my only concern.
I see. What we can do, what I can look into that, if it's meaningful, but at the same time, I want you to learn the course materials too, right? So the final and midterm is kind of a fair thing to know that you are going through the material, you learn them. But that's a fair point. So I make sure that grade-wise, it's kind of compensate for the time that you're spending on that. But more than that, what I'm eager to know is that you're excited for doing the projects, right? Not just doing it for the sake of grades. Because I think this is, not this project, but projects in your course are the main thing that would make your program fruitful and help you through your career as well. So try to think about it that way, and I try to do my part of it to make it grade-wise, compensate your effort, and we take it from there, all right? So I will have more concrete information about what percentage of what it's gonna take and how we're gonna do the grading. And I'm hoping that that update would help you navigate through this.